All right. Well, we'll let people start filtering in, but I'll kind of jump into, what we're doing. Um, Thank you all so much for joining us today for Mastering Motion, Strategies for Teaching Rotational Kinematics and Dynamics. I'll pass it off to our presenter, Tom, in just a moment, but I did want to cover a few brief housekeeping items first. First of all, the recording of this webinar will be available on our website in the next few days, and you'll also be receiving a follow-up email with a recording link, as well as a folder of additional resources and a certificate of attendance. We want to answer your questions during today's session, so please feel free to use the Q&A function or the chat function on Zoom. Josh and myself are going to be monitoring that, making sure we're getting you all answers. And, we can ask Tom if anything pops up that we can't answer, so we'll keep an eye on both of those. And if we do happen to not get to your question, we will definitely follow up with you afterwards. With that, I'll go ahead and pass you off to Tom. Thank you all.
Great. Thanks a lot, Dylan. Again, my name is Tom Smith, part of the engineering education and physics education group here at Vernier. And we're going to be talking about rotational kinematics and dynamics. I know some of you gave us some questions when you signed up for the webinar, so we'll try to incorporate those. We'll certainly be looking at some of the equipment that we would use for teaching rotational dynamics, and but really kind of kicking off the webinar by talking about how we can get set up so your students are successful in learning about this particular topic. Josh Entz is here with us. He and I have been with the company both for about 8 years. Josh, you want to introduce yourself real quick?
I'm Tom's evil twin. I also work here at Vernier. I'm a former teacher like Tom. We both taught physics and engineering in the classroom. We both love hands-on science education, and we love sharing it with people. One thing that Tom didn't mention is that we both are part of the tech support team here at Vernier. So if you ever call or email or chat us up with questions about things, it's likely that you'll end up talking to Tom or I. We love talking to teachers. Teachers make for great customers, and we're happy to support you however we can.
Thanks, Josh. I'm going to go ahead and start sharing my screen, and we'll get this kicked off. So. All the materials that I'm going to be showing today can be found in a shared folder that either Dylan or Josh will put a link to that in the chat for you all. We're talking today again about strategies for teaching rotational kinematics and dynamics. When I was teaching, I taught both conceptual physics and kind of junior, senior level standard physics, and then AP physics. Taught mechanics, calculus-based mechanics. And occasionally in my standard physics class, I would have a chance to dive into rotational kinematics and dynamics, and never had a lot of time to do it. So it was always a little bit rushed, and the result was pretty much less than ideal, I should say, for that class. In my AP class, we had a little bit more time to dive into it and had better experience with that. So part of my my reflection on this topic is going to be kind of contrasting between those two experiences. In having taught with ample time and not enough time this particular topic, and reflecting on that for a few years, I've come up with about 3 different ideas or big ideas that I think affect the ability of students to grasp what's going on with rotational kinematics. And I'm just going to share those with you now, and then we'll come up with some strategies for addressing those. So the first thing that I think is pretty common is that I had an overestimation of what my students understood about radiance. Maybe they'd heard about them, maybe they thought that they knew what that relationship was, but when it came down to really understanding what a radian is and what that means, was a little bit lost on them. So we'll talk a little bit more about that. Certainly, a lot of students had misconceptions about what centripetal acceleration is. I'm not going to get into the whole issue conversation about centripetal force and how you should teach that. A lot of teachers have different approaches for addressing centripetal force. I have my own biases, but really going to focus just on the misconceptions that students have about the concept of centripetal acceleration. And then finally, I think when I was speeding through the process, students often had some confusion between what was centripetal acceleration and what was angular acceleration. And I think that was even true for my AP students when we'd go back at the end of the year and kind of review that whole process. They would have to really kind of address that topic again to get that clear in their heads, which what the difference was between the two and how they interacted. So that's where we're going to go to begin with, and then we'll wrap up with Newton's second law for rotational motion demonstration as well. So with regards to the whole confusion about radians, by the way, let me put a plug in for this book. If you haven't had this before, Teaching Introductory Physics by Ahrens, a highly recommended book. It just provides a lot of good research on what misconceptions the students carry with them, how to address them, and just a good strategy for laying out teaching physics. So highly recommended. Good number of my ideas come from both my experience as well as what I've gleaned from using that book in the classroom. So just wanted to give due recognition there. So, and one of the activities that Ahrens recommends is just really spending some time with students doing a very basic activity where they measure, go find everything that's around in the classroom, measure the diameter and measure the circumference and plot the two against one another and just get a sense for what that looks like. And I have a picture of the screenshot here, but I'll go ahead and pull up the actual data. This was, some data that I just ran the other day. I do have some tips on how to get good data because wrapping a string around something round and then measuring the length of that string is not always the most reliable way to get reasonable data. You can see here that from my data, I ended up with a slope looking at circumference versus diameter of 3.139, 3.14, which is pretty good. I mean, students would have a hard time refuting that there was some relationship with pi there. But let me reduce that for a minute and switch views here just to show you a particular practice for determining this. My screen a little bit larger here so you can see that again. So this was a round thing that I happen to have at my desk. It happens to be a filter for a spirometer. But what I did was I took some painter's tape and I wrapped it around the circumference. And I just very carefully cut the ends of it there so that I could just peel it off and then just lay that right on the my ruler to get a pretty good value of the circumference. I found this was a lot more reliable than trying to use a string to do that. And so just a tip for you to throw in the back of your classroom notes. And then for diameter, I can just put that right on there and read off the diameter there to collect my data. And yet, you know, if you're careful with this, you're actually able to get pretty good data from that. So if you sent your kids off into your classroom with, you know, a roll of tape and a meter stick, they could pretty quickly gather enough data to share to come up with a good understanding of, well, that's where pi comes from. It's that ratio of the diameter to the circumference of a circle. And then to take a little bit of time, let me switch back to this camera if I can. Take a little bit of time to then extrapolate to looking at a portion of the circle and recognizing that the length of the circumference, again, would be 2 pi times the radius. But if you take a shorter arc length of that ratio, the arc length to the radius, is going to be equal to we can use that as an indication of the angle that's demonstrated there. And it holds true for regardless of what the radius of our circle is, that ratio, arc length over radius, is going to be the same regardless. And once they have had a chance to kind of experience that and explore that and own it a little bit more concretely than maybe having just heard an equation in a math class, then you can start to talk about, well, if you have an object moving in a circle, you can use that radian measure in as a unit of velocity, angular velocity. So how many radians per second as you're going around a circle, etc. And just builds a little bit more context for the students to understand what's going on. Okay, so that's the first thing. I want to move next into some of the misconceptions that students may have with regards to constant angular velocity motion. So we're keeping it fairly simple here still, also known as uniform circular motion. So one of the common misconceptions is this idea of the persistence of a curved path. So if an object is going around in a circle and the force that is causing it to move in a circle is removed, what is the trajectory of that object at that point in time? There's a couple of different ways that we can look at this. I've tried it with a curved hose laid down on the table, so I can just kind of put that down here, and this hose is split, which is convenient. That way I can. And the idea being to ask the students the question, you know, what's going to happen when, get my picture straightened out here, what's going to happen when the object rolls past that point? Is it going to continue straight? Is it going to go around the corner still? Just what's going to happen with that? This is a little, we'll go ahead and set this up a little bit for us here. So I have just a drawing on a piece of paper with two options. You know, either it's going to go straight or it's going to go curved. Have the students, you know, interact with this in a real tangible way, so they can see, in fact, that the ball does continue straight once that hose is removed. My personal thinking around this is that the hose and the ball is not where students get hung up on this so much as perhaps a ball and a string, where if you have this ball going around in a circle, being held in by the string, what happens when you let go of the string? My sense is that that's more of where the misconception comes in, thinking that the ball is somehow going to continue to travel in a circular motion as well as a projectile motion. And you could, one thought about addressing it in that context is perhaps to use some video analysis, just shoot some video to show that when somebody lets go of that string, the ball in fact goes straight ahead. And you could arrange that by having somebody at the bottom of the stairwell let that go, where somebody can be looking straight down on the person to get a good video shot of what that looks like. Okay. The next misconception is that the force that causes an object to go in circular motion has a component that is in the direction of the motion, as well as something going inward. Like maybe if you gave them the challenge of understanding, predicting what kind of a force will cause circular motion, they'd probably come up with something like, well, maybe at a 45-degree angle to the direction of motion. And I love the idea of using the bowling ball and the rubber mallet for just addressing just concepts about forces and acceleration in general. Doing that in a webinar was a little tricky, so I managed to find a very good YouTube video. I've already pulled it up, but there is the link to it there. And some of you may recognize the authors of this, biophysics. And if we look at this video, what we're going to see, and what you might do if you don't have your own bowling ball, you could show them this video and just have them predict what is this going to look like how is he going to use this mallet, in other words, to cause the bowling ball to go in a circle. Have them make a prediction up front, and then here we go. This guy is pretty darn talented, if you ask me. So you can see he is really just applying that. We'll watch that again because it's just amazing. 90 degrees to the direction of motion. He has to chase it around to stay on the outside of it there, but and pretty good about just hitting it right there. So again, the idea being that there's not a forward force that he's applying. He is applying a force perpendicular to the direction of motion in order to cause that circular motion. The final misconception that I thought was worth talking about was this idea that we feel when we're in a car going around a corner, we feel like we're being thrown to the outside of the car, and that's a very real, visceral feeling that everybody's familiar with. And how do we go about contrasting that? And I would probably go back to maybe the ball and the string, talking about, okay, what is it that causes the ball to go in a circle? And recognizing that there's some tension in the string pulling in, and then having the students think about that in the context of going around a corner in a car. What is the force that's causing them to move around that corner? And they should be able to recognize with a little bit of coaching that, you know, it's the seat, it's maybe the side of the door pushing against them, maybe even their feet on the floor. There are forces being applied to their body that causes them to feel like they're being pushed to the outside. And you could kind of simulate that if you had students basically push against the side of each other, so that they get that feeling of being pushed to the center, and recognize that that's similar to what they would feel as they're going around the corner in the car. So those are some of the common misconceptions that are worth addressing up front, giving students a chance to start off on a good solid footing when they start talking about this idea of constant circular motion, uniform circular motion, where we're not accelerating tangentially at this point, we're simply accelerating centripetally towards the center. And it's a good time to reinforce Newton's laws in general, that there has to be some force acting on an object in order to cause it to accelerate. And acceleration includes a change in direction as well as a change in velocity or speed. We might spend some time just before we get into labs about this, talking about the nature of this relationship, this centripetal acceleration equal to the velocity squared over the radius, or the angular velocity squared times the radius, and explore some of the nuances there. It's what happens when one increases the angular velocity or the radius. Just kind of thinking about that as a thought experiment. And then we have a couple of labs to play around with here. One is just a simple demonstration. I'll see if I can't do this with, let's see, let's just give this a try. New experiment. And I'm going to do some sensor data collection with a go direct force and acceleration sensor. I only need one graph here. Just want to look at, actually, get back, 2 graphs, but I'm going to look at, disconnect them and connect to my force sensor. There we go. So here I'll go ahead and activate both my x-axis accelerometer, which is in the same direction as my force. I have taped my string onto my hook so that I don't lose it, and I've tied it onto my finger so I don't do too much damage in this process. And we'll go ahead, we have 5 seconds of data to collect, so I'll increase that to 10 seconds there. Yeah. Collect, and then just carefully let that go around a few times, and then I'm going to let it wind around my hand there. So we can take a look at the fact that our force and our x value acceleration are kind of paralleling each other. We could even look at this in a single graph if we wanted to, and just take a look at force versus acceleration. That looks a little messy there, but if I come over here and change my graph options to points instead of lines, we get a better picture of what that looks like. You can see there a pretty good scatter plot of force versus acceleration. And you could use this to, going back to Newton's second law, to determine the mass of this particular sensor. So one application there. The other activity that we had outlined here is using our force, excuse me, not our force and acceleration sensor, but just our acceleration sensor on a turntable. So let me make that a little bit larger so we can see it. The accelerometer has a 3-axis accelerometer, but we're really just interested, you can see there's an X, Y, and Z coordinate system. Y is that direction. X would be back towards my thumb, and Z would be up out of the screen. And we can place that on a turntable. This is all tied up with Lab 20. Looking at this, we can, I'll go ahead and collect some data with this again. So in this case, I'm going to disconnect from that sensor, and I'll start up my accelerometer. And we'll connect with that. And I'm just going to activate the y-axis acceleration on this. So instead of the x-axis acceleration, we'll turn on the y and click on done. And we'll start a new experiment. There we go. So we have our acceleration set up there. Certainly don't need 60 seconds of data collected here, so we'll streamline that to 20 and click on done. And then I have it set on 33 RPM. I'll hit collect, and after a few seconds, I'll just turn on the turntable, and we can see that streaming in there over the 20-second time frame. And then I'm listening to making you guys dizzy by watching that spin around. So turn that back, and we can highlight that section of data and take a look at the statistics to get the average acceleration. And we can equate that with the fact that we're using 33 RPMs to take a look at the relationship between the radius that the sensor's at, and just kind of confirm that that whole relationship between centripetal acceleration and velocity and radius. Now, the lab itself goes through a couple of steps. One would be to change the angular velocity, go from 33 to 45. If you have a turntable that has more, maybe 78 RPM, you could increase that. And then also increase or decreasing, changing the radius, if you will, moving it closer and collecting data for each of those to evaluate that relationship. Another tool that we have available to us is for looking at rotational motion is the Vernier video analysis. And I'll mention at this point that we have a couple, if you don't have a license for Vernier video analysis or Graphical Analysis Pro, we can share a 2-week license for you. So I think Josh or Riley or somebody can put those codes into the chat for you to take advantage of. So I've already gone through the process of setting this up. Basically, this is an old turntable. We have a meter stick in here for our scale. I've set this up with polar coordinates. So our coordinate system is polar, and I've set the 0 axis, the origin axis, right in the center there. And if, let's see if I just go through the add, and we just run this, you can see the data that I've already taken the time to mark the data. But I also am showing vectors here. So this is a position vector and a velocity vector. And the position vectors stream in from the origin. So you can see the radius of the object moving. And then the velocity vector shows the tangential velocity. Let me do that. That tangential velocity of the circle as it's moving around with that shown there. I'll point out while I'm here that I've also adjusted how frequent those vectors show up. So you can adjust that. If it gets too busy, you can always adjust it the other direction. You can also change how long those vectors are to make them visible. So this is one of the stock videos in video analysis as well. So it's a nice tool to kind of reinforce the idea angular velocity, its relationship to tangential velocity there. Okay, so let's see where we're going next with this. Okay, so let me go back just a second just to kind of recap here. So we've addressed some misconceptions associated with centripetal acceleration, and really focused on that uniform rotational motion at a constant angular velocity. And now we're in a place where we can start to jump into some more complex, situations. So, and this is where we want to be careful to, just be very clear that we're talking about a difference between centripetal acceleration and angular acceleration. And one of the strategies that Aaron certainly supports and that I found very effective in the classroom was when I had something that was a little bit tricky, was to actually have students, write down their own version of why that made sense, or just to articulate it to themselves. And then to have a conversation with a classmate just to make sure that they could articulate it, they could own that themselves and clear up any lasting confusion or lack of confidence in how they were understanding the situation. We have a couple of labs, actually just let me just focus on this first lab, lab 21, accelerations in the real world. It has a number of suggestions for activities that you can do where students are going out and collecting data of acceleration and analyzing that acceleration. One of those activities would be finding an empty parking lot and either a car or a bicycle or a motorcycle collecting some acceleration data. Initially, the lab would just have you go straight forward, accelerating forward and stopping, and then going in a circle one direction and a circle the other direction. I will highly recommend that if you take this on with your class, that you have plenty of safety observers in order to keep students from causing any harm or getting into any situation where a student might be injured in the course of this. I will confess that I went out yesterday and collected some data. I'll open that up and share it with you now. So let's go ahead and disconnect from that. And I'll open up my saved data. Where's car acceleration? So this is me going around a couple of corners and changing direction in my truck. And when I got done, thinking that I was in an empty parking lot, I realized that there was a car that had crept into the parking lot while I was doing this. So I just throw that out there as a warning. You really want to have somebody paying attention to the driving, while the other person might be paying attention to the data collection element of this. So safety first and foremost. Thanks. Okay. The other real world application that we highly recommend, and probably safer than driving around in a parking lot, is to go to an amusement park. If you happen to have one available close by, taking the Go Direct accelerometer is a great way to just get some sense of three-dimensional accelerations as you're going around a roller coaster, for example. A lot of different examples in an amusement park for that type of investigation. The next Lab 13 we'll talk about here is really getting into the topic that we're hoping to get to in the first place when we start off on this trip. And I would just I guess encourage you, as you're approaching rotations and rotational dynamics, to take the time to set the stage appropriately so that your students are prepared, ready as best they can be to actually absorb this information and interact with it in a way that helps them to understand rotational dynamics. So, in this case, we're at a place where students can start to think about that angular acceleration, tangential acceleration, if you will, and look at that relationship between angular acceleration, torque, and moment of inertia. It helped me when I was teaching to provide some means for students to viscerally get the sense as to how the shape of something affected how hard it was to rotate or not. And what I would typically do is I would either tape a mass onto a meter stick, or I would give them a balsa stick and a styrofoam ball that was put on the stick so that they could experience rotating it, with the mass at the end where they're having to physically rotate it, or rotate it with the mass close to their hand. And they can see pretty quickly through this really simple experiment that it's a lot harder to rotate when the mass is further away from the point of rotation. That takes a lot more effort. So that gets a little bit to moments of inertia. And then with regards to torque, I would often just have them experience opening a door by using the middle of the door versus the handle. So they get an idea that moment arm really makes a difference when you're talking about things rotating. So that's some sort of a kinesthetic appreciation for what torque is and what that configuration of the mass, how that can affect rotations. And then jumping into Lab 13, rotational dynamics is kind of the target we're headed for at this point. So I'm going to adjust a few things here to show this. Now, I'm going to show this with our Go Direct sensor, but I just wanted to make the point that this is completely appropriate to use the wired sensors as well. In fact, I'll use this to kind of illustrate a couple of things. To attach the pulley wheel on here that we're going to use, we have this as part of our accessory kit. It's just it's like a camera mount, I think is what it actually is. And it just attaches to the pulley and screws into the end of the rotary motion sensor. This is the axis of the rotary motion sensor. This is going to sit on top of a ring stand, and then you would put this pulley wheel on here, actually the other way around, but I want to show you a couple things with this pulley wheel as well. I'm going to change cameras ever so briefly to demonstrate this. And let's see if I can show you this here a little bit more clearly. So the pulley that comes with the rotary motion sensor has kind of two sides of it. One has a slit on one end and the other has a hole on this side. So when I'm doing experiments that cause me to change between diameters of the pulleys, I'm going to use the side with the slit. And I just put a knot in my string and I put that knot on one side and slide it through the notch, and then I can wind it up around the pulley. So if I'm doing this for looking at the difference between the two different pulley diameters, that's how I would do this. If I'm going to stick with, and that's how the first part of this lab works, actually. The second part of this lab would have you just use the outer ring. So in that case, I'm going to actually slip my knot or my string through that little hole and tie it off. You can tape it as well, but I find that tying it is just more secure. And then it's always tied there. I'm not going to lose my string. It's not going to fall off every time I run my experiment. So a couple of tips there for setting the equipment up. In this lab, let me move my apparatus over here so we can take a look at it. Okay, so we have a little hard to see here with the background, but here's my pulley wheel. Here's a disc mounted on top of the pulley. The pulley is actually sitting like this on top of the rotary motion sensor. And the gist of this lab is that we're going to hang a small mass off of the end of this. We're going to use the rotary motion sensor to determine the angular acceleration of the disc as that mass pulls down. And then we'll do that with a variety of different masses so we can look at the effect of the torque, the net torque acting on the system. And then we'll do that for a single disc. Then we'll add another disc to the top of it for two discs. And then finally, we'll use a different configuration altogether, a rod with a couple of masses on it. I'll note that the combination of these two masses is about the same as that rod with the masses attached to it.
Tom, can you make your video window there a little bit bigger for people to see your setup?
Yeah, thanks. So we're looking right in here. This is the disc that we're starting with. Here's the pulley wheel. I know the background is a little bit challenging to see. Here's the rotary motion sensor attached there. And if I maybe just get this set up to collect some data, you can see there's the mass going up and down. And just for the sake of completeness, let me go ahead and collect a quick bit of data. I'm looking at our time and I'm realizing we're pretty close to our expected time of for the end of this webinar, but let me just wrap this up here quickly and collect some data to show you how this might work. So this rotary motion sensor, we're just going to use the default channel, which is the angle. We only need a velocity graph. So here you got angular velocity and 10 seconds is plenty of time, but I won't bother changing it right now. I'll just hit click. I'll let it go. And you can see there's our data being collected. And we're really interested in this section right here to get our angular acceleration. So if we look at a curve fit for that particular section of data, we can pull the slope off of this of 39. So 39 radians per second squared is our angular acceleration for that particular setup. The lab would have you do this for those 3 scenarios and take a look at what effect mass has on that. Of course, there's a little bit of work to do to get to that relationship between torque, acceleration, angular acceleration, and this unnamed at this point moment of inertia. But that's the gist of that particular lab. I think I want to pause here. I'm happy to stay on the line and work through this a little bit more or answer any questions, but I recognize that we're at 45 minutes after the hour. So Josh, any questions we need to wrap up in chat?
No unanswered questions at this point.
Great. Well, I will honor your all time and thank you for coming. Again, if you wanted to hang on and ask any more questions, I'll be glad to stay on the line and answer any questions I can in the meantime. So.
One question you might answer there, Tom, is you can set up the rotary motion sensor as a physical pendulum using the accessory kit. You know, that's a fairly simple setup from what you've got there.
Yeah, you end up because here I can show a. See if I can do that even really quickly. You can basically turn this sideways like so, and then this becomes a physical pendulum if you mount it on the axis there to rotate like this. Okay, well, thanks again for everybody coming, and hope you got some information from this that was useful to you. If you, the resources we put in the folder were all designed around the GoDirect sensors, but if you have LabQuest sensors and use Logger Pro, I'd be happy to share those same resources with you in that format. Just reach out to physics@vernier.com and mention that you would like those resources in that format, and we'll get them to you.
Thanks again, everyone. We'll send a follow-up email to you once everything's kind of ready to go. And if you need anything, please feel free to reach out. All right. Bye, y'all.
Goodbye.